Welcome to RC Scientific. In this video we explain static torque twist and show why it can vary among different chassis models. The chassis comprises motor, gears and drive shafts with the axis pointing in driving direction, while the other axis of the axles and wheels point perpendicular to it. The motor tries to accelerate the car. However, in certain situations, counterforces can occur that hinder the car from acceleration. This can happen when driving against an obstacle or at steep slopes. In such cases, the motor cannot translate its torque into forward motion. Instead, the motor with its gears and drive shafts gets blocked by the wheels, axles and differentials, which leads to a bending of the chassis. The elastic counter torque produced by the bended chassis generates an equilibrium with the static torque produced by the motor. A weaker chassis, which is characterized by a smaller stiffness constant C, leads to a stronger bending or deflection. The stiffness of the chassis can be determined by producing a known gravitational torque that leads to a measurable deflection angle delta phi. The stiffness constant C can then be computed from the deflection angle delta phi, the gravitational mass and the lever arm L at which the mass is placed with respect to the center line of the chassis. Let's now determine the chassis stiffnesses of three different RC model cars and compare them with each other. For the MST model car, known mass, gravitational acceleration, lever arm and deflection angle yield to a chassis stiffness of 0.27 Newton-meter per degree. The same measurements are repeated for the Traxxas TRX-4 chassis. Here we see that it has a higher stiffness than the one of the MST chassis. The highest stiffness was found for the chassis of the Absima CR3.4. Thanks for watching RC Scientific.